Casual conversation cartoon curriculum, very concise and relatively correct, as simple as possible, as soon as possible. A&P, it's chapter 4. This is our second little installment right here. Again, looking at the graffiti that we've used in class, please remember once again that the general practice questions give you all the information that you really need for the foundation of the chapter. Oh, yeah. But we use the graffiti to try to illustrate it, to make it come alive, to make it stick in your brain. So let's go to the next step right here. The next step right here is talking about transport across a cell membrane. So in this diagram that we've used in class, that we've created in class, the box represents a cell, stylized cell, schematic cell. And we're going to talk about passive and active processes for moving things across the membrane. So membrane transport. With passive transport, ATP is not used by the cell. It's free. It just plain happens if the cell membrane will allow it to happen. With active transport, the cell has to pay for it in the form of ATP. So ATP energy has to be used to move something across the cell membrane. With passive, there's a gradient, and something is moving down the gradient. That's why it's free, because second law of thermodynamics basically says things go down gradients. That is, things go from order to disorder, something high to something low, generally. So in this situation here, we can talk about things moving from high altitude to low altitude, like water going downhill. Things can go from high pressure to low pressure, high voltage to low voltage, high concentration to low concentration. There are several examples we've used in class. Over here, you're doing something really weird. That is, you're going from low concentration to high concentration. You're going upwards. You're pumping water up a hill. So that's the reason why with active transport, there has to be a source of energy and there has to be a mechanism to make something move, in essence, in the wrong direction. Okay, over here for passive membrane transport. Right off the bat, we've got something like diffusion, simple diffusion. And this bracket right here represents concentration. And rather than using numbers, let me just use the icons right here. Large brackets means higher concentration, small brackets, lower concentration. And the direction of diffusion is from higher concentration of a material to lower concentration of that same material. Simple diffusion is represented by things such as oxygen moving into a cell from higher concentration outside the cell to lower concentration inside, because the cell is using up the oxygen on the inside, keeping the concentration low, and you are breathing in to provide oxygen for the body to eventually provide it for the cell. At the same time that oxygen is diffusing into the cell from greater to lesser concentration, carbon dioxide is diffusing out of the cell from greater concentration of carbon dioxide to lesser concentration of carbon dioxide. And there's a greater concentration of carbon dioxide inside because the cell is making carbon dioxide. And there's less carbon dioxide outside because you are exhaling and you're getting carbon dioxide out of your bloodstream, therefore out of your body. So simple diffusion right there, pretty straightforward stuff. Osmosis, a bit more complicated. Osmosis is the diffusion of water through a semi-permeable membrane. And that's what this silly little picture down here is supposed to remind us of. Here we have an example of something that is freely permeable. Things move across the cell membrane, no hindrance at all. Impermeable means nothing moves across the membrane. Things are trapped in or they're trapped out. Semi-permeable means some things can move back and forth and some things cannot. And a cell membrane is a semi-permeable membrane. Now, water is relatively freely permeable to the cell membrane. However, there are gates called aquaporins that we'll talk about later on that can be provided. Now, water moves from greater concentration of water to lesser concentration of water. That's why it is diffusion. But the concentration of water in a solution is sometimes represented by something called tonicity. Now, tonicity is a relative term, and so therefore it has no meaning unless you compare it to something. And it's being compared to intracellular fluid. And in our story about osmosis, we're going to talk about what's water doing. We're going to find out that water is going to go from greater concentration of water to lesser concentration of water. Now, the terms that we use to represent the concentration of water, unfortunately, really directly refer to solute concentration. So the word tonicity refers to the solute concentration in a solution. Now the solutes, of course, you remember the things that are dissolved in the water. So let's say we put a cell, a normal cell, whatever that is, into an isotonic environment. Now, tonic refers to the amount of solute, iso means same, and it means that this environment around the cell has the same concentration of solutes and thereby the same concentration of water as the cell does. Therefore, if the solutes cannot move across the cell membrane and only the water does, then water will diffuse into the cell and out of the cell in equal rates and the cell will not change its size or its shape. If, however, you put a so-called normal cell into a hypotonic environment, hypo means less and tonic refers to solute, so in this case, the environment has less solute, thereby, by reverse thinking, more water than the cell does. Since the solutes cannot move across the cell membrane, but the water can, the water will then go from higher concentration outside the cell to lower concentration inside the cell, and the cell will get larger, perhaps even bursting, as in the case of hemolysis, where a red blood cell in a hypotonic environment will have so much water coming inside, it'll balloon out from its normal biconcave disc shape into a sphere, and then eventually perhaps rupturing. Yeah. The other situation right here is hypertonic. Hyper means more, tonic refers to solute, so this would be an environment in which there's more solute than the cell has inside. Less solvent, more solute. And if you put this cell in this environment, and of course the solutes do not move across the barrier, only the water will go from greater concentration to lesser concentration of water, and the cell will lose water, lose volume, and could shrivel up. As in the case of crenation, in which a red blood cell is in a hypertonic environment, it loses its water and it loses its beautiful biconcave shape. So again, reminder, tonicity is relative to the intracellular fluid, and the cell is the standard that everything's being compared to. And that was an example of osmosis. Facilitated diffusion. In facilitated diffusion, there has to be some kind of a pore gate mechanism to allow diffusion to occur. So these things, which could be called channels or gates, they're embedded inside the cell membrane. You'd imagine it would be an integral protein. And things will move through these gates if they're open and if there is a concentration difference. Now, there's two general types of channels or gates right here. Some of these things are called gated and some are called leak. Leak channels are always a little bit open, sort of like a window you can't completely shut, so things will move across it regularly. Gated channels specifically can open or close. And because of that, you get a lot of control right here. Now, gated channels can be open or closed usually by two methods right here. There's a chemical method and a voltage method. A voltage change or disturbance might cause a gate to open or close, or the presence of a specific ligand might cause the gated channel to open or close. So again, once the gate has been opened some way, somehow, it's still the concentration gradient that decides what direction things will move. An easy example of something like this is the channels that allow sugar to move into the cell. If you open up that channel, sugar can go from greater concentration outside to lesser concentration inside. You'd expect that to be the case because you eat food to gather sugar, among other things, and the cell is using that sugar, so the concentration of sugar inside the cell should be relatively low versus the outside, where it should be relatively higher if you're eating regularly and such. Once again, an aquaporin is an example of a water gate. So again, an example of facilitated diffusion. Real quickly, let's go over the idea about active transport. In active transport, ATP energy has to be used by the cell. The cell pays for this to happen because they're breaking the laws of nature, which say things go from high to low, not low to high. A good example of this is active transport illustrated by the sodium-potassium pump. The sodium-potassium pump takes sodium from the inside of the cell and throws it outside. causing the concentration inside to be small, concentration outside the cell to be large. At the same time it's doing that, it's grabbing potassium outside the cell and pulling it into the cell, making the concentration of potassium inside large and potassium concentration outside low. Again, the sodium and the potassium are going up their gradient. They're going the wrong direction. But the pump can do it because it is powered by ATP. ATP, of course, which came from most of it came from the mitochondria because it had oxygen, it had sugar, it created carbon dioxide, it created water, and it created ATP. Moving on down here, vesicular or bulk transport. In vesicular or bulk transport, the cell can actually invaginate or evaginate and allow materials to move through. If it's moving into the cell, it's called endocytosis. If it is throwing things outside the cell, it's exocytosis. There are three common examples of endocytosis. Something called phagocytosis, where a large object is brought in. Then there's pinocytosis, where a small object is brought in. Or receptor-mediated endocytosis, where there is a receptor on the surface of the cell membrane that recognizes an object, attaches to the thing, then pulls it inside.